Hi everyone. In this lesson we're going to look at dimensional analysis. And so dimensional analysis is sort of an interesting way of combining math and science. Dimensional analysis. And so we have several equations, and we've talked about measuring, and we've talked about unit conversions. And one thing you have to keep in mind when you're dealing with measurements is you can only add things if they have the same dimension. So adding, dimensions must match. And we'll even take that a step further, and not only do the dimensions have to match, the units will have to match. But we're just gonna focus on the dimension part of that for now. So for instance, if I have a length of say 10 centimeters, and then I have another length of 20 centimeters, and I add those two up, we know that we get 10 centimeters plus 20 centimeters is a total length of 30 centimeters. Dimensionally, I have a length, I have a length, I have a length. And so there's this idea of just looking at a dimension to check to make sure that what we're doing is valid. And so if you see me put a measurement in brackets in this section, this is contextual, but this bracket is an operator that says take whatever in there and return the dimension. So 10 centimeters has a dimension of length plus 20 centimeters. 20 centimeters has a dimension of length, right? So what I'm saying is there's equality here with this operator. The dimension of 10 centimeters is length. The dimension of 20 centimeters is length. The dimension of 30 centimeters is also length. You'll notice I took a length plus a length and I got a length. I did not get length plus length equals two lengths. A length is a length is a length, right? The dimensions are all the same. So dimensionally, we don't care what the numbers are. We don't care how many things we're adding. What we care is what dimension we are adding, right? And so there's an equation that we'll learn fairly shortly. In fact, most of you probably already know it, that change in position or displacement, which is delta x, is equal to velocity times time. What I want to do is I want to go through there and actually make sure dimensionally that that's true. If two things are equal, they have to have the same dimension. Well, change in position is a length. So the dimension of delta x is L. The dimension of velocity, okay? Well, velocity is a length per time, L over t. Time has dimension of time. So we can see that we take time divided by time, those cancel, and we get length equals length, and that's a true statement. Okay. Now a note on the symbols that we use for dimensions. For a dimension of length, we use L. For a dimension of time, we use a capital T. For a dimension of mass, we're going to use a capital M. For a dimension of, say, temperature, just to differentiate it from time, we might use the Greek letter theta. We'll basically be limited to length, time, and mass, so won't worry about that too much. So let's look at an equation that we will eventually learn. It's the impulse momentum theorem, and it says force times time equals change in momentum. Delta, if you see the delta, the triangle, it's a Greek letter delta, that means change in. So up here, delta x meant change in position. Down here, delta p means change in momentum. So delta is change in. We want to find what the dimensions of force are. So to do that, we're going to take the dimensions of each quantity. And I'm going to tell you that momentum, p, is equal to mass times velocity. So with that in mind, we should be able to figure out the dimensions of force. And so dimension of force I don't know, so I'm just going to rewrite that. Dimension of force times the dimension of time, right? I'm going to take the dimension of time. Well, the dimension of time is t. T pops out of that. Equals delta p. Well, p is equal to mass times velocity, and a change in is just a difference, right? And so we're going to take a mass times a velocity minus a mass times a velocity. So we're really just going to look at the dimension of momentum. So the dimension of mass, m for mass, and v is L over t, length over time, because it's a speed. And then I can go ahead and divide both sides by t. Now be very careful when you do that. When I divide by t over here, that's the same as multiplying by 1 over t. And so what I'm left with is force, the dimension of force, because I haven't taken it out of the brackets yet, is equal to mass times length divided by time squared.